Imagine this. You wake up to the sound of your phone buzzing. Bleary-eyed, you check the news. The headline staring back at you makes your stomach drop. Asteroid detected, with potential to strike Earth in 2032. It sounds like science fiction, right? A plot ripped straight from a disaster movie. But this isn't fiction. In late 2024, scientists from the Panoramic Survey Telescope and Rapid Response System, PAN-STARS, based in Hawaii, detected a fast-moving object cutting across the night sky. They named it 2024 YR4, an innocuous-sounding designation for what might have been a world-shaking event. This asteroid, initially estimated to be between 45 and 70 meters in diameter, was projected to pass uncomfortably close to Earth in the year 2032. Initial orbital models placed its odds of impact at nearly 3%, a terrifyingly high number when you consider that even a 1% impact probability usually prompts close international monitoring. For comparison, the asteroid Apophis, which caused a media frenzy when it was discovered in 2004, had a maximum predicted impact probability of less than 1% before being ruled out. YR4, in contrast, sparked immediate global concern. Here's the problem. With spotting a new asteroid, you can't tell where it's going with high accuracy until you've observed it over time. When it comes to space rocks, trajectory is everything. With only a few days of observation data, orbital paths are fuzzy, uncertain, imprecise. It's like trying to predict the landing point of a football thrown from the other side of a stadium, while blindfolded based only on a single second of flight. This is where ground-based telescopes initially stepped in, providing more data points. Observatories in Arizona, Chile, and even Italy quickly zeroed in, refining the orbit. Yet a crucial mystery remained. What was this asteroid made of? Composition affects how sunlight heats the asteroid's surface and how that heat is re-radiated, a phenomenon known as the Yarkovsky effect. This subtle force can nudge an asteroid's orbit over years or decades, sometimes enough to alter its path significantly. If YR4 had a dark, carbon-rich surface that absorbed more sunlight, it could be slowly drifting toward a trajectory that intersects Earth's orbit. If it had a high spin rate or was tumbling, those thermal emissions might be uneven, further complicating predictions. But ground telescopes can't see those thermal signatures clearly. Even radar imaging from the Goldstone Deep Space Communications Complex, which bounced radio waves off YR4 to map its surface, couldn't answer the big question, just how dangerous is this rock? That's when NASA and the international astronomical community made a bold decision to interrupt the schedule of the James Webb Space Telescope, the crown jewel of space science, and turn it toward a threat much closer to home. The JWST was never meant to track asteroids. It was built to peer into the earliest light of the universe, to detect atmospheres of far-off exoplanets, and to capture the birth of galaxies billions of years away. And yet, here it was, about to focus on a space rock just 12 million kilometers from Earth. The pivot was dramatic. Engineers at the Space Telescope Science Institute had to halt planned deep-field observations and recalibrate the JWST's tracking system. After all, YR4 was moving far faster across the sky than distant galaxies. They used its mid-infrared instrument, or MIRI, a tool designed to capture the faint heat glow of dying stars and icy moons, to instead measure the subtle thermal radiation from this rogue rock. Over the course of multiple orbits, JWST observed YR4 across infrared wavelengths between 5 and 28 microns, collecting enough data to construct a thermal model of the asteroid's surface, and the results were sobering. The sea. Asteroid was darker than expected, indicating a carbonaceous composition, meaning it likely absorbed more sunlight and was subject to a stronger Yarkovsky drift than previously modeled. But thanks to JWST's sharp thermal vision, scientists could now estimate its size at 57 meters, with a margin of error under 5 meters. That's large enough to cause citywide destruction if it were to impact, similar in scale to the infamous Tunguska event of 1908, when an explosion in Siberia flattened over 2,000 square kilometers of forest. Furthermore, JWST's data helped measure its thermal inertia, how quickly its surface heats up and cools down, which confirmed that the asteroid's surface was dusty and porous. This meant the Yarkovsky effect was likely pushing it, ever so slightly, away from Earth. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. As JWST's data poured into servers back on Earth, experts at NASA's Jet Propulsion Laboratory fed the thermal and orbital parameters into their Sentry 2 impact monitoring system. This system runs millions of simulations to predict possible future paths, taking into account gravitational interactions with planets, non-gravitational forces like the Yarkovsky effect, and observational uncertainties. What they saw was a massive relief. The risk corridor had shifted. The new trajectory showed that YR4 would likely pass Earth at a distance of over 400,000 kilometers, roughly the distance to the Moon. Still close, still worthy of tracking, but no longer on a collision course. The world exhaled. But the story doesn't end here, because YR4 is just one of over 30,000 near-Earth asteroids we've catalogued, and there are likely hundreds of thousands more we haven't yet seen. The decision to use JWST to observe this threat wasn't just a brilliant act of scientific improvisation, it was a blueprint for the future. It marked the first time a telescope designed to explore the beginning of time turned its gaze inward to protect the present. It's one thing to know that the James Webb Space Telescope, JWST, observed asteroid 2024 YR4. It's another to understand how. Because what happened behind the scenes was nothing short of a cosmic ballet, a feat of astronomical choreography where science, precision engineering, and raw human ingenuity all collided in a race against time. This wasn't just a telescope pointing at a rock. This was an instrument designed to stare billions of light years into the past, now being retooled on the fly to protect the present. Let's rewind to the moment the decision was made. When initial trajectory models raised alarm bells, there was urgency. Asteroids don't wait. The longer astronomers delayed, the faster YR4 moved across the sky, and the harder it became to track. But using JWST wasn't as simple as flipping a switch. This telescope orbits the second Lagrange point, L2, a gravitationally stable zone 1.5 million kilometers from Earth. It was built for stillness, not speed. Its gold-plated 6.5-meter mirror is so sensitive that even minor shifts in temperature could cause data corruption. Its instruments operate at cryogenic temperatures, below -266 degrees Celsius, to detect the faintest heat signals in the universe. Now, engineers were being asked to swing it toward a fast-moving, heat-radiating rock within our own solar system. Tracking a near-Earth asteroid like YR4 presented a technical problem. Unlike distant galaxies, which stay relatively fixed in position, YR4 was moving fast. From the telescope's vantage point, the asteroid zipped across the sky at a rate dozens of times faster than its usual observation targets. To keep the asteroid in frame, JWST had to pivot, literally, reprogramming its fine guidance sensor to follow a dynamic track, recalculating pointing models in real time. Engineers at the Space Telescope Science Institute in Baltimore worked overnight, coordinating with scientists from NASA, the European Space Agency, and planetary defense teams across multiple time zones. And then there was MIRI, the mid-infrared instrument. Think of MIRI as the telescope's heat vision, able to detect temperatures as low as -200 degrees Celsius. For this asteroid, it was perfect. While visible light telescopes rely on sunlight reflecting off the surface, MIRI sees the heat the asteroid emits. This is key because different types of materials, metallic, carbonaceous, silicate, radiate heat in different ways. The thermal fingerprint of an asteroid tells you what it's made of, how fine or coarse the dust on its surface is, and how quickly it heats up during the day and cools at night. It's like being able to feel the texture of a rock without ever touching it, just by measuring the way it radiates warmth. The data JWST collected wasn't just beautiful, it was actionable. Over a 24-hour period, scientists watched YR4 rotate, analyzing how the infrared signal fluctuated. Those changes revealed its rotation period, roughly 7.8 hours, and its shape, which turned out to be elongated, something like a cosmic football tumbling through space. Even more importantly, MIRI captured minute variations in surface temperature from one side to the other. By comparing those variations with models, scientists could infer that YR4's surface wasn't solid rock. It was something looser, more porous, a carbon-rich rubble pile, perhaps. This told them a lot about its history. Unlike dense iron-rich asteroids formed in the cores of early planetesimals, rubble piles are more like cosmic leftovers, loosely held together by gravity after billions of years of impacts and collisions. This matters, because the structure of an asteroid determines not only how it heats up, but also what would happen if it ever entered Earth's atmosphere. A monolithic asteroid might punch through and explode on impact, creating a crater. A rubble pile, by contrast, might break apart mid-flight, like the Chelyabinsk meteor in 2013, which shattered in the sky above Russia with the force of over 400 kilotons of TNT, damaging buildings and injuring over 1,500 people without ever touching the ground. But JWST didn't just answer questions about this asteroid. It helped build a framework for the future. By combining the mid-infrared data from MIRI with radar data from Goldstone and optical tracking from ground-based observatories, astronomers created a multi-layered model of YR4's orbit, spin, composition, and thermal inertia. This kind of layered dataset had never been assembled so quickly or so precisely. It's like taking a fuzzy satellite photo of a moving car and turning it into a high-definition, slow-motion breakdown of make, model, weight, and speed. Right, before it enters a tunnel, and it's all connected to the bigger picture. In 2021, NASA launched DART, the Double Asteroid Redirection Test, which slammed a spacecraft into the asteroid moon Dimorphos, proving we could alter an asteroid's trajectory with a kinetic impact. Now JWST has stepped in with the next step, understanding which asteroids to target, when and how. It's one thing to punch an asteroid, another entirely to know if that punch will do anything. Imagine trying to stop a snowball mid-flight by throwing a baseball at it. If the snowball is tightly packed, you might knock it off course. But if it's loosely made, you might just explode it into 1,000 dangerous fragments. Knowing the difference is the line between success and catastrophe. JWST's data changed everything. Within 72 hours of the observations, the updated models showed that YR4's trajectory had shifted. The thermal push from solar radiation, now better understood thanks to the new data, had nudged the asteroid away from Earth's danger zone. The chances of impact dropped from nearly 3% to effectively zero. The world's most advanced space telescope had, in a very real sense, saved the day. But let's not pretend this is a happy ending. Because the truth is, 2024 YR4 was just one rock in a vast, silent storm. Every night, telescopes scan the skies for thousands of near-Earth objects, many of which remain hidden, faint, or too small to detect until they're dangerously close. Some of these are tumbling chunks of metal from the early solar system, others are icy remnants from long-dead comets, and among them, one might not miss. What JWST proved is that we now have the tools, not just to look outward into deep time, but to turn inward and defend ourselves. And this raises a bigger, more haunting question. What if the next one can't be nudged away? Imagine a scenario, not 100 years from now, not in the realm of science fiction, but one that could unfold in your lifetime, maybe even in the next decade. A telescope scans the sky and spots an object. It's small, fast, and unfamiliar. The models are run. The results are terrifying. There's a 1 in 10 chance it will hit Earth in 6 months. Now ask yourself, what happens next? This is no longer the premise of a disaster movie. Thanks to missions like DART, the keen eyes of the James Webb Space Telescope, and international planetary defense protocols quietly developed over the past 2 decades, we now stand on the brink of something remarkable. A world in which humanity can look up at the heavens and say, for the first time in history, we're not helpless. But make no mistake, the road here was built on centuries of trial and error, myths and meteors. Let's step back, way back. In the early 1800s, the idea that space could be dangerous was pure heresy. Comets were thought to be omens, meteors were dismissed as atmospheric phenomena. It wasn't until 1803, when a meteorite shower rained down on the French town of L'Aigle, that scientists were forced to accept that rocks could fall from the sky. The field of planetary defense was born not in labs or observatories, but in fear and disbelief. Now fast forward to the 21st century. Near-Earth objects, or NEOs, are catalogued daily, space rocks that orbit close to our planet. Some are harmless, passing within a few million kilometers. Others, not so much. The infamous Apophis asteroid, discovered in 2004, was once believed to have a disturbingly high chance of hitting Earth in 2029. While later observations ruled out that impact, the fear it triggered became a wake-up call. It led to real investment in early warning systems, impact simulations and strategies that have only now begun to mature. Enter JWST. Its sudden pivot to analyze asteroid 2024 YR4 marked a new milestone in planetary defense, not just in capability, but in global coordination. Unlike other telescopes which require clear skies and nighttime conditions, JWST orbits in darkness, free from atmospheric interference. Its ability to peer into the thermal signatures of objects like YR4 gives us insight no radar or optical system can replicate. But perhaps the most important lesson from this incident wasn't the data itself. It was the reaction to it. Within days of JWST's observations, a coordinated response rippled through the scientific community. Emergency virtual briefings were held between NASA, the European Space Agency, JAXA in Japan, and even non-spacefaring nations with high-stakes interests. Plans were reviewed, scenarios tested. Could a kinetic impactor reach the object in time? Was a gravity tractor feasible? Should evacuation be considered if a smaller fragment broke off and entered a populated zone? For the first time, the world was treating an asteroid threat not as a curiosity, but as a crisis. It was the response time, not just the detection, that marked progress. And yet, for all the celebration, a haunting reality looms. Not every object can be intercepted. Some are too small to track until they're hours away. Others, like long-period comets, come screaming in from the Oort cloud. Icy, ancient behemoths that move so fast, they outrun most early warning systems. And unlike asteroids, which orbit relatively close to the Sun, these comets can appear with little notice, leaving days, sometimes mere hours, to react. What's more, Earth's surface isn't equally vulnerable. An impact in the ocean could trigger mega-tsunamis. One in a city could level millions of lives. And then there's the worst-case scenario, a large enough impactor striking land or sea with enough energy to alter the climate. Sound far-fetched? It's not. 66 million years ago, an asteroid about 10 kilometers wide crashed into what is now the Yucatan Peninsula. The result was the Chicxulub impact, a blast equal to over 100 million megatons of TNT. It extinguished 75% of all life on Earth, including the dinosaurs. We call these extinction-level events, ELEs, and while statistically rare, they're not impossible. In fact, the geological record suggests they've happened several times in Earth's history. Humanity has only existed for a blink of cosmic time. We've never faced one, but someday we might. And that's where the philosophy of planetary defense starts to change. From reaction to prevention. It's no longer just about nudging space rocks or sounding alarms. It's about weaving asteroid detection and response into the very fabric of civilization, into budgets, policies, education systems. Think of it like wildfire response or earthquake drills. We prepare for what might happen, not because we expect it tomorrow, but because ignoring it invites disaster. Already the seeds are being sown. NASA's NEO Surveyor mission, set to launch in the late 2020s, will scan the sky in infrared specifically to find potentially hazardous objects. Ground-based programs like Pan-STARRS and Atlas work every night to detect sudden intrusions. And now, with JWST in the mix, we've added a deep space sentinel to our arsenal, one that can peer into the soul of an asteroid and tell us what it's made of, how it spins, and whether it's truly a threat. But perhaps the most important shift is cultural. For millennia, humans looked up and feared the sky. Now we look up and watch. We analyze. We prepare. Because we finally understand something simple and profound. The cosmos isn't just vast and beautiful. It's unpredictable. And in that unpredictability lies both danger and destiny. So here we are, on the edge of a new era, one where astronomy meets survival, where data could mean the difference between a near miss and mass extinction. And as we build the tools to defend this pale blue dot, one question grows louder. Will we be ready next time? So, what now? The asteroid didn't hit us. Crisis averted. Headlines fade. The world moves on. But should we? Moments like these, when humanity stares down a threat from the cosmos, are more than just scientific milestones. They're mirrors. They reflect who we are, what we fear, and how we respond under pressure. And more importantly, they ask us to imagine who we could become. When JWST locked its infrared gaze onto asteroid 2024 YR4, it wasn't just scanning rock and metal. It was probing the future. It was a warning and a rehearsal, because this time we had days, weeks, even months to prepare. But next time, it might be different, faster, closer, deadlier. And yet, we didn't panic. We observed. We responded. We learned. That in itself is extraordinary. In the grand sweep of cosmic history, Earth has always been vulnerable. For over 4 billion years, this planet has been bombarded, reshaped and scarred by celestial debris. Our moon, it's a memorial, in plain sight. Each crater a reminder of past collisions that could have ended everything, if they had struck just a little closer. And now, for the first time, we possess the power to see it coming, to push back. That shift is more than technological. It's philosophical. Imagine a civilization that no longer sees itself as passengers on a fragile world, but as custodians of its destiny. That's what planetary defense represents. It's the idea that space isn't just a frontier, it's a responsibility. That defending Earth is no longer a divine hope or random chance. It's a choice, a science, a commitment, and maybe, just maybe, this isn't the end of the story. Maybe it's the beginning. Think about it. The tools we build to detect and deflect asteroids, they're the same tools we'll use to build outposts on the Moon and Mars. The same propulsion systems that can nudge a rock away from Earth could one day send cargo to Europa or return samples from Enceladus. The same collaborations between nations that averted disaster in this instance might become the foundation of a unified spacefaring species. What if every threat is a test? Not from the universe itself, there's no conscious intent in asteroid trajectories, but a test of us, of whether we can rise beyond fear and division, whether we can see the bigger picture, one where humanity isn't just on Earth, but of Earth, and responsible for it, because here's the truth no one likes to say out loud. One rock, that's all it takes. One uncharted object, 10 kilometers wide, traveling at 30 kilometers per second. No warning, no escape. A planetary reset, but we don't have to accept that fate. We are not powerless. In fact, we are more prepared than ever. The incident with 2024 YR4 was not just a lucky break. It was proof of concept. That early detection works. That international coordination is possible. That JWST, a telescope designed to study the dawn of the universe, can also protect our present. That's the beauty of space science. It's never about just one thing. It's about understanding our origins and securing our future. It's about gazing into the distant past while anchoring ourselves in the here and now. And maybe, in some poetic way, that's the role we were always meant to play. We are creatures of the earth, but children of the stars. We were born from stardust, shaped by gravity and carved by time. And now, as we learn to shield this fragile world from the chaos around it, we take our place, not as victims of fate, but as architects of survival. So, the next time you hear about a near-Earth object, don't roll your eyes. Don't dismiss it as sci-fi or fear-mongering. Remember this moment. Remember YR4, because it was real, it was close, and it could have been worse. Instead, let it remind you that we're in this together, floating on a pale blue dot, surrounded by silence and stone, armed with only our intelligence and unity. And maybe, just maybe, that's enough. If this journey through asteroid warnings, deep space telescopes, and planetary defense opened your eyes, share it. Hit that like button. Drop a comment below. What do you think we should do to prepare for the next cosmic visitor? Your voice matters because in this vast universe, every perspective brings us one step closer to understanding and protecting our shared home. Until next time, keep looking up and keep whispering to the cosmos.